Yes. Mm-hmm. Hi, Kristen. Nice seeing you connected. Did everyone got the files in? Did everyone got the files in the email for? Good, good. So they're not always named appropriately, but if you look for the files names starting from like 1 to 3, it will be approximately the same subjects as we do this year. So the let's wait if more people will join. So the plan is to have this presentation, then we will learn another piece of software maybe for 2 weeks, and then another 2 weeks will be for the project. So there will be, in addition to presentation next week, there will be two more. So next week on Gaussian, in 2 weeks on VASP, and then in 2 weeks on microscopic mini research projects. And I will try to spend substantial time in suggesting um, steps on research projects, but please consider to start selecting objects that can be part of your research project right now, because as time goes by, everything will be quicker and more squeezed. So by now you do have some general ideas what can or what cannot be done about strengths and weaknesses of the approaches we do, and you may design the models for the projects. Um, if it is metal organic complex or molecule for reaction, combustion, or catalysis, it's quite easy. But if you are dealing either with large biological molecule or infinite chunk of nanostructure, then one needs to think ahead how to chop and select fragment of interest that would be representative part of the problem. Okay, I think we are past 5 minutes. I suggest we start. So we are um, close to completion of the chapter on Hartefok, and in these slides that are shared, there are links on YouTube. They are similar recordings of similar lectures a couple of years ago. There are little adjustments, and I hope that there are improvements, but general core of material is the same. So if you do not, you need to compare, you can just take the link and check how it looks like. So I believe that we do have sufficient presenters, 1, 2, 3, 4, 5, to cover most important subjects, and please consider to um, present maybe a little bit more than that is literally stands near your name, especially if there are no neighbors. Like for Gianta, I think it is enough. For you, it is more than enough. For Kristen, it is okay. And for Mahima, I do not know. She may want to show a little bit on DOS, but maybe if she is will skip it. Um, well, I'll try to convince her. But Janice, if you look on subjects that are below molecular orbitals and tell a little bit more about them, would be reasonable. Um, okay. So after I will be done with theory background, we need to complete things that were done. Oh, I have forgotten. Please try to compose the slides for the presentations. There were requests to postpone the presentations to the Wednesday instead of Monday. But anyway, I would like to ask everyone to submit the slides by Sunday night, Sunday midnight, like 12 p.m., so that I do have time to glance over them and make some suggestions. Please, if you do not reply anything, I consider it as agreement. If you have some arguments against, please type or say. Okay, so I would expect to see so, and the reason for me to see your slides ahead of time, there are two reasons. One is to provide feedback, because it is a big responsibility in these slides, in the following sense that the presenter teaches the rest of the class, makes a refreshment. And second thing, when it will be time for presentation, as we did once, if everyone will try to share screen, there will be delays. And if I combine all of them and share systematically from one place, it will be more vivid, organized, and quicker. Okay, so after we are done with equations today, we need to cover this couple of commands: compose density, spin density, and potential out of CubeGen, and look over the like click right buttons to look over this moving charge analysis. For some applications, it is a good thing. It is reasonable. Okay, so what to expect at the end of today's meeting? So especially if you hate equations or do not want to focus, to spend your intellectual focus on them, here are just two slides which summarize where we should arrive, and this is something that one can take as a take-home message. So in this chapter, we did nail down ions, and we do not change positions of ions. We are looking only for electronic problem, and electronic wave function of many electrons is represented as the Slater determinant of one electron molecular orbitals. And the only thing that we can do to find right molecular orbitals that will satisfy specifics of the molecule and distribution of electrons are expansion coefficients. So how to represent molecular orbitals in terms of atomic orbitals. And in some sense, Hartree-Fock theory is a theory of finding expansion coefficients of molecular orbitals. So in the slide that I'm showing right now, this vector, multidimensional vector C sub I, is column of expansion coefficients for all atoms and all atomic orbitals in the molecule. And these values inside this coefficient will be different for each I, for each index I, for each molecular orbital. So we are solving matrix equation to find these expansion coefficients. And the main question, main task for me is to explain where this equation comes from, how to formulate it. So what is this F capital, what is this S capital? At the end of the previous chapter, we did play robots. We did geometry optimization by hand. We did formulate the flowchart diagram for finding best interatomic distances. Now we do need to set up a flowchart diagram to find the C set of expansion coefficients for each molecular orbital. And there are objective reasons why this problem cannot be solved at once. So there is a specifics, and I'll tell you during our meeting, why this problem needs to be solved again and again several times until where the output of one iteration serves as an input for another iteration until it converges. So getting these two pieces of information, what is the matrix equation for expansion coefficients and flowchart for solving this equation in a so-called self-consistent way is the goal of the meeting. Please feel free to stop me anytime. Not just stop and do not say any other word, but stop for clarification of any parts of our today's material. And let me quickly go over a review of what we did last time, because neither one of us is spending 100% of time in deriving equations and thinking about them day long. So it is very natural for human brain to just wipe off this information from the brain, and now we need to bring this context back in the discussion. So we are going along this little plan, and it also looks like a flow chart, but it is a different flow chart. It is not the one that we will get as a result of our consideration. We are in the meeting number 14, and we need flow chart for solving Hartree-Fock equations. And this is just logical steps, how we collect ideas and connect them together in order to, I wouldn't say derive, but set up, explain internal logical connections between units of the Hartree-Fock theory. So we did start from Slater determinant and provided background from spin theory to get this functional form of antisymmetric product. Then independently we considered mean field of the influence of all electrons, all but one electrons on the remaining electrons, and then we covered so-called variational theorem. And then we observed that the antisymmetric form of Slater determinant brings, so Coulomb is positive repulsion and exchange is negative attraction of electrons. I cannot, it's not legitimate to say this word, electrons do not attract, but there is a term in Hamiltonian that term in total energy that has negative energy, and it corresponds to stabilization of the system. And it's one of the achievements of the theory that Hodge-Fock theory that makes it useful. And then we combined multi-electronic wave function into one electron equation for one electron wave function for orbital through this mean field Fock operator. And then after we combine this all components together, we will get the equation and flowchart how to solve it. So one electron orbitals are multiplied by each other in the same term, same way as elements of matrix are multiplied to get the determinant. And through practicing this so-called flated determinant, one is getting terms with minus when one swaps orbitals. And this is critically important for stabilization of molecule, for getting terms with negative. The idea of mean field is that electrons that are already sitting on a molecule repel new electron that we are combining in. And another aspect that we didn't discuss, if I bring in one more electron, it changes the rest of electrons as well. And then it will change the background field that will affect new electrons. So one needs, if we bring in several electrons, each of which is the distributed wave function, each of which is repelling each other, they need to find optimal distribution in space that minimizes energy. And if you are not doing dynamics, if you're doing it as a static calculation with only one electron problem at a time, then one needs to repeat this procedure again and again until they settle in a more comfortable way. Once upon a time, we did play the Wheel of Fortune for the guessing the word of expectation value. So when we need to extract energy out of Hamiltonian, we convolute it with Bryan-Ket wave function, and we can do it partial convolution. So make an average over second electron and keep it as an operator over the first electron. And when we did this, once we do it for an average over second electron, and then it will be operator that acts on first electron. Then we did average over first electron, and it will be operator that acts on second electron. And this equation is the closest to the actual Hartree-Fock equations that are being solved in the Gaussian software when we solve it. But before we go to this cycle-wise self-consistent procedure, to this flowchart, we do need to bring in the variational theorem and expansion in the basis. So variational theorem is that energy of ideally found multi-electron wave function will be always smaller than energy of wave function that has been perturbed. Psi? What? Plus delta. Psi. And in so few more things. We are setting up a hierarchy of the objects. So we start with positions of ions, then we remember that there are atomic orbitals on each ion, and then we superimpose atomic orbitals on each ion into molecular orbitals that depend only on one electron. And in this hierarchy, only expansion coefficients can be changed. So last time we tried to practice to decompose total energy that originates out the cool electron interaction that originates from expectation value procedure for all electrons for Slater determinant, and we did found that there is a term that takes minus sign, and this is what is called exchange of two electrons. That on Feynman diagram language it is this swapping of the electrons, and for theory it's very important that there is a negative term that stabilizes molecules. And what else? And then we decided to tell about the tell about average influence of all but one electrons on the electron number 1. So this black box is average influence of rest of the electrons. Here in this diagram it's only electron number 2. And then this black box is kind of operator that changes structure or function of the first electron. So it's Coulombic repulsion. And if one does the same for the term in the total energy that corresponds to exchange, it will be like electron comes in orbital number 1 and exits in orbital number 2 because it exchanges state between one of the electrons in the background. So by now we have finished a review of what was done last time and starting new part. So Douglas Hartree did the theory that solved that gave practical way to find electronic structure of molecules with many electrons, and he did this mean field theory very good, but he did forget to take into account the fact that multi-electron wave functions should be antisymmetric, and in some textbooks there are examples for energies and properties of molecules like interatomic potentials computed based on Hartree theory, and they look not realistic. And then another scientist, Vladimir Fock, he basically introduced the antisymmetry. He told, take Hartree theory and bring Slater determinant inside, and then it fixed a lot of problems and results become very relevant. I did have an interaction as an undergraduate student with former student of Vladimir Fock when I was in the undergraduate program. So let's focus. I'll skip a couple of slides. Let's focus on the way how the molecular orbitals are composed out of atomic orbitals. So generally, Hartree-Fock theory must work independent of atomic bases. And if we look into the computational aspects, the results of the calculation should stay the same if we construct molecular orbitals not from correct hydrogen-like atomic functions, but from something different. And when you were launching Gaussian calculations and browsing through Gaussian options, you saw that there is an option to change basis set. So if calculations are absolutely correct, if basis set is very good and has many states, then results will be independent of selection of basis set. If we are limited in computational resources, humans can find some tricks to do partial basis set with good or bad functions, and then it creates either speed up of calculations or increment of precision. So these chi sub a atomic functions are never taken literally as they should be in hydrogen atom. There are approximations to deal with these functions. So please try to if you were doing something else or taking a nap, now it is time to concentrate a little bit. There will be a couple of entry points which seems reasonable and important. So the atomic functions. I will introduce three types of bases. So one is ideal atomic hydrogen-like ideal. So if we take the I'm getting thousands of SMS messages. So if we look for S and P orbitals for solutions of hydrogen atom, they look like exponential centered at position of ion. I better withdraw it. So when we are looking on this S function, S orbital localized on atom number 1, R1, it will have this sharp peak in the vicinity of the ion R1. When we have another atom centered at position R2, then it will be a sharp exponential peak at position where position of electrons is equal to position of ion R2. The sharp peak originates from this absolute sign in the hydrogen wave function. And if we do have p orbital, then we do not have charge density literally at the center of the atom. So R1 multiplying by this raising function, so it is a little bit plus to one side from atom and a little bit minus to other side of the atom. And you may develop a little some questions, and you may decline to understand what is written because one is expecting orbitals to be three-dimensional. But here we take only one dimension and projecting things on x component of the position of the first electron. These functions with some normalization constants in front are literal solution of hydrogen atom. Those are ideal atomic functions. But this sharp peak, sharp cusp in the S functions brings a lot of complications in the computation and in math. If function has a discontinuity, if it has sharp peak, one cannot apply derivative, and a lot of computational procedures fail. Oh, hello you. Happy to see you connected. So atomic wave functions have sharp peaks, and they are computationally complicated. And there is a trick to replace the function with sharp peak in the center by function that will look very, very similar everywhere at the when function is away from the position of ions. So have it smooth and a little bit different in the exactly near the position of center of atom. So in some sense, the exponential of the absolute value of difference between position of electron and position of nuclei can be replaced by exponential of the negative of the square of their difference. So by putting some coefficients up front, these two functions can be made equivalent. And this is what is done in Gaussian software, and it is the reason why the software is called Gaussian, because the atomic exponential to the power minus square of something is a Gaussian function. So atomic wave functions, atomic orbitals, are replaced with Gaussian functions. And this trick makes computation much more efficient. It is why it was possible to create the software at the end of 70s, beginning of 80s, and why it becomes so popular and we are still using it. So atomic wave function is replaced by Gaussian functions. This is a really good plan for studying molecules, chemicals, small objects that are localized and not continuous. But when we are looking for extended nanotubes or graphene sheets or infinite bulk of semiconductors or metals, these atomic wave functions are not as efficient. When we are looking for so-called periodic structures, the features of electronic of wave function are repeating in the same pattern again and again on the log distance. And basis set of atomic functions is replaced by so-called basis of plane waves. And Kristen is very much aware of this basis because of the PChem class, and Janice will be hopefully exposed to this idea very soon in a couple of months. So part of the PKM class will be on plane waves. In about a week from now in this course, we will stop using Gaussian and start using software WASP, which is completely based on use of the plane waves. But from the point of view of Hartree-Fock theory, either one of these functions is only a basis, expansion basis for solving equations. Yeah, I'm trying to draw this function each year, and for the plane wave, it's like oscillating function which can have imaginary non-real values. So we need to the room internet connection so bad. I will take help from James and Kristen. Oh yes, Jayanta, please consider to watch the recordings, right? If right now it's hard to hear. So we are focusing on expansion coefficients which contain basis functions, which are in some sense for chemists are atomic orbitals, but telling basis functions is more correct. So provide to combine atomic orbitals into molecular orbitals. So one adds together several atomic orbitals, so better say several basis functions with expansion coefficients and get molecular orbitals. Since we are connecting atomic and molecular orbitals, we need to have at least two indices. One index for molecular orbital and another set of indices for atomic orbitals. So before today, we already had an equation, one electron equation of the reduced Hamiltonian acting on the unknown molecular orbital. But this function was for continuous orbital as function of continuously changing position. It is possible to do, but it is not optimal. The whole progress of applied math, wherever computers help to solve engineering problems and science problems, are based on the concept of expressing continuous functions in the specific basis. So our goal right now is to go from molecular orbitals defined as distribution continuous changes in space into language of expansion coefficients. And then if we have if our orbitals are transformed from continuous objects to set of discrete functions, then we do need to convert our equation from differential equations for continuous function into equation for expansion coefficient. So if we have discrete set of expansion coefficients, which we can write as a vector, then it will be some sort of matrix equation for expansion coefficients. As soon as we done with it, we will be basically done in this chapter. So here are the concepts that we are planning to combine together. So we used to have chapter concept of background charge from all but 1 to 1 electron. We have a concept of antisymmetry. We have 1 electron reduced operator. We will need to refresh concept of matrix element, expansion coefficient in specific basis functions, and then we will combine all operators and all these concepts into a flow chart. We'll recover this, we'll recover this. Okay, I think it is a not bad slide. So we have performed an averaging of the Hamiltonian over all but one electrons. So we composed one electron operator. And if we do it correctly, it does contain the kinetic energy of this one electron, the attraction of this one electron to all nuclei, and then contributions that we were drawing with Feynman diagrams. Repulsion of this last electron from the rest of the electrons, and I would say stabilization, attraction of the last electron to the rest of electrons. So how to bring this equation into the matrix form? So we already used to have this equation. Fock operator acts on unknown molecular orbital, and O, and O, and those are molecular orbitals that we know that we can plot if Gaussian is working properly. But there is a secret. This equation, which is originally formulated as differential equation, is solved not as a with continuous derivatives. It's solved in a specific basis. And for transferring the equation into a specific basis, we need to review the concept of orthogonality. Please stop me anytime, because I do not see the faces, I do not hear the voices, and I can get too excited and go too quick or too slow or lose connection. So a little connection of the audience following these things is needed. I'm trying to explain things, but I need your feedback. So, any questions at this point? Okay. So we need to review the concept of the orthogonality. So if we do have a good basis set, so if you have a function chi 1 star of R and chi two of R without star. And then I decide to multiply them and integrate over dr. So let me ask Kristen, what will be the result if chi1 and chi2 belong to a set of belong to a good basis set, if they are solution of quantum problem? Kristen, would you please guess the answer? If we do have set of good basis functions that are likely solutions of quantum problem, eigenstates. So we have set of eigenstates, and then we take two of them with indices not coinciding, for example, first and second function. And then we multiply them and integrate over independent variable. What will be the answer? Huh? If the indices will be the same, then the answer will be 1. But if the indices are different, please type so that we have, or repeat. 0. Yes, yes, thank you very much. Thank you, Kristen. You did save this meeting. So in good basis set, when the indices are the same, answer is 1. If indices are different, the answer is 0, and it is called orthogonality. But, and just a second, and this is correct if you have atomic orbitals centered on one atom, right? S orbitals, p orbitals, d orbitals orthogonal to each other. But if we do have atomic orbitals on ion 1 and ion 2, there is no proof, there is no guarantee that they will be orthogonal. So if you have ion 1 and ion 2, and for example, s orbital and on ion 1 and p orbital on ion 2, and we multiply them and integrate. This integral, the meaning of this orthogonality, is measure of overlap. So if they overlap and do not have opposite phases at the place of overlap, the integral will be between 0 and 1. So atomic orbitals localized on different ions are not orthogonal. And I believe it is typed here. Not orthogonal. So if we need to convert all equations into basis set, we need to take into account this measure of non-orthogonality. And this matrix S, mu for atomic orbitals mu and atomic orbital nu, can take values between 0 and 1, and this is the measure of non-orthogonality. So everywhere where in regular traditional quantum mechanics we would have either 0 or 1, here, because we work with molecules in atomic basis, we need to have this measure of non-orthogonality, which is called overlap matrix. Okay. Number of slides is not 0, what we need to look through, but we are coming very close to the end in sense of logic. We have all components. Whew. Any questions about overlap matrix element? Okay, nothing. Now we do need to express the one electron equation in terms of expansion coefficients. So we need to go from molecular orbitals to expansion coefficients. So we need to formulate an equation that will help to find expansion coefficient I, comma, nu between molecular and atomic orbitals. And if you were not following in details, now it is a second time when I invite everyone to look with attention. then one can skip or be less concentrated on next slides, but this one is important. So our goal is to find equations for C I nu. And the definition of conversion from between molecular orbital to atomic orbital is this summation, superposition. So why don't we take this summation and plug it into our one electron reduced equation for molecular orbital. So we are going to plug it and then do a trick to remove atomic orbitals completely, to keep only C expansion coefficients as unknown. So if you do agree with this idea, then you can lean back and relax for like 10-15 minutes. I will provide a little bit of technical details which are just implementation of this idea. So we plug in this definition into this equation. Okay. So the black, let me check if it is typed in a better way. No, I'll better go over this handwritten slides. So the black font, black drawing corresponds to result of plugging in the molecular orbital into equation for molecular orbital. So this green highlight are molecular orbitals. Our goal is to describe only this expansion coefficients. So this equation is bad and ugly in the following sense. It does have the atomic wave functions chi sub mu, which we do want to eliminate. So we want to get rid of the wave function from the equation. And the way of removing wave function is available through practicing orthogonality. So if we multiply wave function by another wave function and integrate, typically one is obtaining either 0 or 1 through such integration. In this situation, we will get s orbitals. So in addition to our original equation, I did plug in. So equation doesn't change if we multiply left and right part on the same term. So I multiplied original equation by this integral by this chi sub mu and integration sign both left and right part. So if I perform integration of these atomic wave functions with index mu and index nu on the left part, so index mu and index nu on the right part, then we will get rid of the atomic wave functions, and the only thing that we will keep here will be expansion coefficients and new objects, matrices, matrix elements. So please stop me if I'm too quick, or if it is if you're trying to follow but it is too boring. if you are not stopping me, I consider it as this material is extremely funny and everyone is happy to listen further. So when I combine these atomic functions and F orbital together, note that it is not allowed to swap the order between wave functions and orbitals without penalty. So I'm composing here an object composed of the integration, one atomic wave function, another atomic wave function, and orbital between them. So it looks like expectation value, but it is expectation value corresponding to transition from atomic orbital mu to atomic orbital nu. So it's mathematical procedure of combining two functions and operator into a number. But since under indices mu and mu, we assume all atomic wave functions on all atoms in the system, this will be a matrix. So this will be a matrix corresponding to one electron Hamiltonian acting on the molecular wave function. And this matrix element of this Fock operator is called Fock matrix. So this is what we have on the right side. On the left side, we do not have any operator. We have just wave function mu without star, wave function mu with star, and we do integration over independent variable. If our basis would be ideal, this term will be either 0 or 1. But since atomic orbitals localized on different atoms are not always orthogonal, this combination will be replaced by this S matrix, measure of non-orthogonality, overlap matrix. So we are moving from differential equations for continuously defined molecular orbital to discrete matrix element. Okay, we did it. So plugging in definition, then multiplying left and right part by this convolution term, practicing the orthogonality. So we plug the stuff from the left and right, and performing the convolution, which will bring us the Fock operator on the left side and overlap matrix on the right side. If I replace integration of two wave functions with bra and cat, one can define them this way. So bra of mu, f cat of mu, and the overlap matrix is bra of mu and cat of mu. And we didn't modify the summation on the left and right. So we are very close to completion. Nothing new here. So this is already the equation that is being solved in the Gaussian software. I just want to wrap it up in a better notation and explain what is going on. So this box is matrix F mu mu. This box is matrix S mu mu. And the notation when we have summation over one index, for example, mu equals 1, mu equals 2. So when we have this summation, then matrix and then vector does correspond to the row by column rule. So if we do have elements of this matrix in here, so summation means that we are taking subsequently elements from the row of matrix and column of the vector and multiplying and adding them together. So this row by column rule is explicitly expressed in these summations. So we do have summation over nu, matrix, and then vector. Summation over nu, matrix, and vector. And this idea of expressing Hartree-Fock equation was introduced by Clemens Ruthan. I do not know if he is alive by now, but he survived his 100th birthday, so he was one of the longest living scientists, and it is his contribution to bringing Hartree-Fock theory into computers. So he was one of the first scientific programmers, and he got this idea while visiting opera in Chicago. So if we do have this equation, then set of expansion coefficients can be stored as a column vector. So first index is atomic orbital. I want to put letter A. And second index is molecular orbital. So if we are looking for molecular orbital number 1, we can write it as C1 vector, just to have a notation in a little bit simpler form. And if we do have matrices, Fock matrix and overlap matrix, we also can save them, store them in either write all elements in the matrix or just use fat bold font letter F and bold font letter S. So in some sense, we are moving from Hartree-Fock to Ruthan. And if we write it in the elements, it means Fock matrix multiply by expansion coefficient vector equals eigenenergy of molecular orbitals times the overlap matrix times expansion coefficient of molecular orbital number I. At this point, we do not need to do anything else. But 70 years ago, people were trying to solve equations like this by pen and paper. And you know that in order to solve eigenvalue matrix problem, one needs to bring everything to the one side of the equality sign, just subtract left from right, make it equal to 0, and find determinant of the remaining matrix. So if you multiply by elements, it will be element of Fock matrix minus unknown eigenenergy minus times element of the overlap matrix, and continuously for all of this multiplied by a vector of unknown molecular orbital vector. Good. So Fock matrix times molecular orbital expansion coefficients equal unknown eigenenergy times overlap matrix times expansion coefficient. And in order to solve this equation, one finds determinant of the subtraction between Fock and overlap multiplied by eigenenergies. By solving such equation, one is getting eigenenergies of molecular orbitals. So it seems, please keep relaxing, do not wake up. There will be one more point of becoming active, but it didn't start it yet. Maybe 5-10 minutes and we will be done with the theory. So it seems on the first glance that what we have now gives us everything. We have Fock matrix, we have Fock equation. By solving it, we are getting molecular orbitals and energies of orbitals that we can plot as form of density of states and draw as convert them into balloon-style figures and do science. Is there any challenge? Is there any difficulty? Why we cannot do it once? Or I'm having the answer right in the question. So we cannot do it once because the shape of the Fock orbital does depend on molecular orbitals. So if we remember when we defined Fock matrix, it does depend on where the rest of electrons, all but one electrons, are sitting. So this is not matrix done once and forever. As soon as we find set of molecular orbitals, Fock matrix, Fock operator do change. Therefore, if we extract these expansion coefficients from this solution, use them to reset, to reformulate this big F, and try to diagonalize it once again, the results will be different. And it is careful and beautiful at the same time. Careful because we do not have solution in hand, although time is expiring, and beautiful because we can just solve it iteratively. So if one uses the output of diagonalization as input to formulate Fock matrix and then repeats again and again, there are ways to prove that the molecular orbitals will converge to such values which will correspond to what happens in nature. So they will stop changing after several iterations. And we need to quickly go over this procedure. So finding eigenvalues of Fock operator and eigenvectors, one can plug them into definition of Fock matrix. And so here I think one may wake up and look. So this block corresponds to this F minus epsilon S capital equals 0. So from this equation one finds set of eigenvalues and also one is getting set of molecular orbitals. So to start this procedure, one should have some initial guess of molecular orbitals of the previous step to formulate the Fock matrix at the beginning. But then after we have initial guess, maybe it's step 0, and then first step of finding molecular orbitals, one can compare the total energy that we compute by expectation value of total Hamiltonian with Slater determinant, and check if this total energy at previous step and next step agree to each other. If they are very close, we stop the procedure. If they do not coincide, we take molecular orbitals from Fock matrix diagonalization. So we take shapes of orbitals, which is stored in molecular orbitals, recompute Fock operator and Fock matrix, and go into diagonalizing of the Fock matrix. And then again, compare if this gave the convergence. And as soon as convergence is achieved, one can calculate properties such as electronic ionization, affinity, density of states, and other things. So with this, we are done with theoretical part. I will happily answer any questions. And I suggest we will go to the practical part, which will be quicker than previous time. We will just look on the files from previous lab and try to make this total density and spin density images. So let me invite everyone to open either terminal if one is using Mac, or MobaXterm if one is using Windows PC. And let's log into, in one window, log into Photon, in another, just stay on a local computer. So if I go into Google and type CubeGen, it will prompt these keywords. So they're not designed here. So we need CubeGen O density equals SCF. Let me type it. Gen. Then I'm giving the form check file, and then CHK. So now I'm going to open Gauss view and plot this file. But before I'm doing it, let me ask, what is your opinion? What is density, and why do I need it? Density. Let me ask Janice. Do you have any vision or ideas? Which density is meant here?
So I am pretty sure that it deals with electron density on each of the groups, and where exactly electrons are located in the molecule that you're studying. This can be useful for knowing how to react with such a molecule. Yeah.
Okay, okay. And suppose we have a molecule with only one electron and one molecular orbital. What would be the equation? How to find the density distribution out if the orbital is known?
So it would just be the exact equation for it. I'm sorry.
If we do have, let me maybe draw the equation. So if we do have the is the way. So if you do have the system with only one electron, for example, it is hydrogen atom, and we know that the electron is in the s orbital.
Yep.
And we do know the shape. We do know the shape of the molecular orbital for this s state. So we have phi, let it be phi 1 of x, y, and z. Three-dimensional map.
Yep.
How to convert this three-dimensional map for molecular orbital into the density? What should one do with it?
Oh gosh. So to transfer it into density, I believe you have to do a convolution of some sort. I'm trying to remember here exactly. You had said it in the slides, I know that much. I would have to look back at the slides to remember exactly. But you do have to do some form of integral regarding the atomic orbital and its sort of shape.
Okay, okay. You didn't tell anything wrong. You are on the right path. You're just trying to. I see you are trying to keep a little bit undefinite saying to avoid possible error. So let's check. Maybe other class members can suggest. So how to convert wave function, molecular orbital, into density. Kristen?
Right now, I can't think of anything beyond it. I know you talked about it in the slides. I have to look back at.
Let me reformulate the question. The word density is a little bit scareful. If you know wave function and you do need probability distribution, how to convert wave function into probability distribution?
Oh, I know. So you can take the absolute value and square it.
Aha, yes, yes. Kristen, sorry, I think you were ready to answer. I have no doubts. Just Janice was quicker in verbalizing it. Yes, yes.
I'm sorry. Yeah,
That,
I
that,
apologize.
that's
I
okay.
apologize.
And if one wants to be very practical and meticulous, one can write it as psi star times psi. So because this star complex conjugation compensate imaginary part, but absolute value square is as good as this star thing. Okay, okay, and I'm very happy we started this little discussion. The standard interpretation of quantum mechanics prompts us to speak about probability density, but computational chemistry uses a little bit different interpretation. So if we do have probability of electron to be in this area, in specific area, to be a little bit more probable than in other area, then one can interpret it. Again, it's a still controversial statement in the big science, but for practical purposes, we believe that instead of probabilistic interpretation that there is a higher probability to be here and there, we will tell just electron is distributed in space and it has more density in this area and less density in the other area. And this interpretation of the wave function and orbital in form of density is not absolutely correct philosophically, but is very fruitful for applications. And later on, very soon, we will see that one of the best theories of the 20th century, density functional theory, is based on this interpretation. Make sense?
Mm-hmm.
If you have more than one orbitals, we just, if you have like two orbitals, we then have phi 1 absolute value square plus phi 2 absolute value square. And more general, all occupied orbitals, all occupied molecular orbitals, absolute value square added together, give this probability distribution that electron is sitting somewhere, or in this interpretation, practical interpretation, that there is more charge density, electron density in a certain place of the space. So please practice of plotting this thing. So I'm opening Gauss view. Going into open cube, available cube files. Density, cube, open. Clicking on results, surface contours, and there are surface actions, new surface. So before I click on new surface, I may modify. So there is a different threshold ISO value for molecular orbitals and for density. So if I take this number small, then the balloons will occupy more space. If I take this value large, the balloons will occupy less space. And So I used larger value of the isosurface, and now it shows like the balloon covering basically the whole molecule. Now I am clicking hide surface, changing the value by, let's say, 0.04 to be aggressive. New surface. Now the balloon should cover even more space. Okay, smaller value, bigger balloon. And if I take this much surface, it does take smaller space. So it shows that the density of charge, probability of electrons, is bigger around a group of atoms and is substantially bigger around oxidizing atoms like oxygens. I am going to download this file to the local computer and open it with other software, Vesta, because you and Kristen have some conflict with Gauss view, or Gauss view is by some reason is not working. But we are finishing from next week, or as soon as you do presentations, we will do other software, and Gauss view will be possible to use, but not mandated at all. Okay, so I'm looking for PWD. No. Oh, yes, it is on this photon. SCP. Everything that ends with Q. Space period. And I probably mistyped the name of the host. So the some people do not like Gauss view, even if it is available, and some people feel very comfortable with Gauss view. Later on, when we will be using other software, there will be an opportunity to convert formats of the output of other software into Gauss view format, or into this cube format, and plot it in the same way as one was doing in Gaussian. So even output from other pieces of software. So bonds new from titanium to oxygen. Okay. So now it looks more practical. So around titanium, it takes this shape specific for d orbitals. Although, since there are all d orbitals there, maybe it should be more homogeneous. And then it is balloons around oxygen. Janice, were you able to follow and plot?
Yes.
Okay.
Yep. The electron density plot is up on my screen.
Okay. Kristen, were you able to plot?
Well, I'm able to follow on with the manual stuff, but my Gauss-Q doesn't show anything, and I don't have that stuff.
Okay, so you do have two options that I was showing previous time and will repeat. So one option is, let me bring it up. Okay, so one option is to, without watching the image, one can, in Gauss view menu, make save image file. Do you see it? So you select save image file. And click save. It will take some time. It's not instantaneous, but with a little of patience, it will create the image. So it takes about a minute. 27%. And then in the directory, there will be a file with graphical information. So this is the option number one. And I will complete it and show that it does work. The option number two is download the cube file and try open it with your favorite reliable software like Avogadro or JMOL or Vesta, which if it is a software on your personal computer, it should work. So I do see file density.tiff. So it was created, and if I download the file to local computer, I can insert picture from file and take the image file that was created on the photon and downloaded it as the image file. So even if I do not see the image by my eyes, if some visual things do not work, it's still possible to do. Kristen? Yes?
I'm also doing the second method. For some reason, Gauss-Q won't let me save image files, gives me an error message.
Huh.
It fails to allocate.
Interesting. Let me check in your directory. So you are probably in lecture 13. Potential cube, spin cube. Okay. So are you downloading these files to your local computer?
I just did. But
Okay.
when I open them in JavaScript, it won't let me save the image file.
Let me just quickly check if I can open files from your directory on by Gauss view. Open. Up. Up. So the file is loaded. It doesn't show error. And if I try to do a surface, action, do surface. Yeah, it does work. So your file is healthy. It should work as well on the local computer. And which software are you using locally to plot it?
I haven't tested it locally yet, but I'll plan to drop a Docker.
Okay. Okay. Let me do the same. So I was able to plot orbital with Avogadro. But I do not see immediate ways to plot charge density. So instead of taking charge density, it's individual objects. It wants to read the whole form check. So I think if we need to plot charge and spin density, and ESP maps, Avogadro is less suited. Kristen?
Yes.
Would you share your screen?
No.
Yeah, thank you. So please change the background by going into view, and then in the middle there is a set background color. And set it to white. Yes, okay. And now on the right panel, scroll down to about 35, where chemically important orbitals are, the border between occupied and unoccupied. So on the right side panel, there is a list of orbitals, right? So about 35. You see they're highlighted with green. If you select one of these green orbitals, and then at the, yes, exactly. Okay. Okay, so at least you can do orbitals. And there is a button configure, so it allows to change the isosurface value. So by changing isosurface value, it may show larger isosurface, smaller balloons. Okay. So and let's probably try to use JMOL and Vesta if by some reason you need the density, spin density, and ESP map. Yep. Thank you. Let me check. Oh, my pleasure. You? How things are going at your side? Okay, so you were able to plot both density and spin density. And did anyone got success in plotting ESP map?
I tried it, but it didn't look like anything.
It it happened to me today as well. Let me. I'll try to share the screen and quickly try to redo it once again. So
I tried doing it in Navigator as well. It did not.
no, in Navigator it will not work for sure. Windows.
The rest of them worked in Navigator though. So. Though I tried running it in Gauss view and it just did not want to run.
So if I open form check, and from the form check, go to surfaces and contours. Make a new cube. And select ESP. So the operation of the CubeGen is also available to do in the mouse operated commands, but they work substantially slower and work as a little attempt to try human patience. So it's okay. Electrostatic potential. I remember what should be done. Maybe we will not be we will not complete it today, but one needs to create both total density and ESP map, and then merge them together, because ESP map needs a reference point to be built on. So it is not a standalone object, but it takes density as an input. Density. Okay, I'll show it another time, doing a little more preparation. But let's do last thing that we can quickly quickly do right now is click on charge.
Oh, I
yes?
actually got it.
Oh, okay. Can you please share screen?
Yeah.
And explain. I think it would be really great.
Okay. Okay. So it looks like you just need to turn up the density to about 1. That was the only thing I changed with it. But it doesn't show the exact color mapping, but it does show the general mapping. You can see this, right?
Yes.
Dr. Kinnan?
Yes.
Okay. Super. But yeah, so all I did was just change the density value to 1. So I guess the ISO value is a little bit too small, and so it's causing the potential geometry to blow up, which might have caused some issues.
So you think it is just value of the ISO value of density?
I think just changing the density to 1 should help. Do you want me to create a contour based off this, or?
With contour, it will be, I think, less visible. But please play, and if you get success, report it during your presentation. It will not take much time, but it will be very appreciated by everyone in the class.
Okay, understood. Do you know how to get the color mapping on there?
Let's discuss it after the class.
Understood. Okay.
I used to do in the past, but let's check it over. So last thing that we can reliably do right now, immediately, is.
I think your Festa can easily open it.
Pardon me?
Festa, you can open with Festa.
Oh, ESP map with Vesta, right? Can you show it? Can you show it? Just share and show how you do it.
Can you see the screen?
Yes, please.
Yeah, so you just open the cube file. Then it automatically display in the Festa.
Mm-hmm.
Can you see my screen?
Yes.
Yeah,
yes.
just open it.
Okay. Okay.
Just open it. Yeah, here.
Mm-hmm.
Then here is the.
Okay.
Yeah.
Yeah. Very good. Very good. Yeah. Thank you. And we quickly do last thing because it's time is running out and maybe you have more plans. So if you take one of the output files like log or form check, they all have this information, and then click on the results and charge distribution. There will be
long are you planning to stay helium? Whole week or? Not 2 days is already Friday. So in this week, because now I have like a cheap window which we are going to do tomorrow morning, but a better one comes next week, Tuesday.
Okay, so if you select charge distribution, you will get this little menu that gives option. First option is Mulliken, shows color range, and then you just
Next, I mean, for me, anything is fine. I don't care, but I'm just telling that I'm going to measure only next week, then I don't need to do this one, right? I can directly use the better window.
So you are clicking on this tabs in the menu, and it appears to show the numbers near each atom. So it tells if it has deficiency of electrons or additional electrons. So if it is if you're not speaking, please turn off the microphone.
I have only one sample.
If you're not speaking, please turn off the microphone. Mute the microphone. Janice? No, it's not Janice.
Okay, anyways, I think it would be good practice.
You?
To do it.
Is it at your side?
Just break them.
So, Janice, were you able to get this numbers for?
Yes, I was able to get the numbers and everything.
Okay.
So I'm looking at the same thing on your screen as on your screen. So.
Okay. Yes. Very good. For you, I'll try to find what can be done in the other software. One of the things, it writes down this information in the log file, but I'll try to find the way to analyze it in graphical form. But I think we are done with our program for today. So are you okay to make presentations on Wednesday rather than Monday?
Yeah, that's fine.
Okay, you? Is it okay on your side?
So since now I am going back to work, so actually my time is not so flexible now.
So Monday or Wednesday, which time is better for you?
I prefer Monday, but if it's Wednesday, it's fine.
So you is it possible this time on Wednesday or not?
Yes, can I do the first one on Wednesday? Can I be the first one?
So tell me what would you prefer when you are busy? When do you need to leave earlier or you can start later? Just.
So I can start. Can I start first and then maybe I leave earlier?
Oh, okay. Let me check. Wednesday start first and leave earlier. Yes. Okay. Yeah,
okay.
It's possible. Please consider to send draft of preliminary version of slides Sunday late evening, late night. So I will glance through if it needs to be improved. And on Monday there could be, I wouldn't say guest, but co-teaching. Svetlana Kivina, Professor Svetlana Kivina may give some additional comments to Gaussian, because next week we will finish with Gaussian and start new software.
Okay.
Okay.
And could you send us the Google Sheet so I know what's the topic?
Oh yes, you don't have it?
I don't have it.
Okay.
Yeah.
So let me do it right now while we are on the connection. So try to pull. Yes, I did send it. It should work. And let me click myself that it works. Yes, it does. And did you get the template examples from previous year?
Yes.
Okay. Okay. Very good. Very good. Okay. Then I think we are done. If everyone is welcome to disconnect.
Thank you.
Thank you.
Thank you so much.
Yep. Have a nice week.
You too.
Thanks. Bye-bye.